Okay, so that is the plan of the talk, and this is something which I'm sort of, some of you maybe, so some of you, a large part of it could be a repetition, but nevertheless, so this is something mathematically I'm trying to, this is the program which I'm trying to for quite a few years, and I really, and for this particular meeting, I'll be very happy to, if some physicist can find something useful or some physical intuition can be provided to me, which will be great. So that is one of my motivation to present this thing here. Although for okay. Now, so here I even need not emphasize the importance of non-commutative mathematics. So all of us are sort of, I think, convinced. So the two branches which I deal with are the quantum groups, and another is of non-commutative geometry, which many speakers have already dealt with. And quantum groups also, starting with the very first talk of Vaishan. Now, I'd say the successful marriage of the two are yet to be done. I mean, there are lots of examples, but perhaps a more full general theory and even encompassing locally compact quantum groups and so on, are still on the way. I mean, it's not yet fully done, but of course, the last 2 decades or so, there have been fantastic work, and we now understand much better. We have a quite general theorems about equivariant spectral triples and other things. Now, for that, what I mean that to have these two things together, more precisely, the equivariant spectral triples, and I mean, indeed, Allen formalism, some of the mathematicians who constructed such things as Chakravarti, Paul, Gianni, Dabrowski, and Sitarz, many of them are present here, and then also Hayek, Nesvet, Tusset. But this is, of course, nothing like an exhaustive list. There are other who have done and still doing work on it. And on the other hand, Shan Majid himself and Hronovich, who started these things, and they, of course, have a slightly different formalism of equivariant geometry, which Shan presented in his talk, and so on. So there are several such set up by now, and with interactions, overlaps, and so on. Now, my motivation or my question is the following. I basically turn around and ask the following question: that if you give me a geometry, and if you give me a spectral triple, what are all possible quantum symmetries of it? I mean, when I ask all for convenience, for mathematical and otherwise, I restrict to the formalism of compact quantum group. That's why I put the compact in bracket, but philosophically this is not necessary. I mean, one should, in principle, can ask the same questions in maybe purely algebraic framework or some more general analytic framework like locally compact quantum groups and so on, but I restrict myself to the compact quantum setup. So my question is that what are all compact quantum group actions on the underlying system algebra for which the given spectral triple is equivariant? And if it exists, I'll call it the quantum and symmetry group, and so on. And as one expects that this should have some important role in understanding both mathematically the geometry, the underlying non-commutative geometry, and even one can extend or hope to extend to this purely matrix-based setup, the quantum matrices of Riffel and so on. Some work, I've done some work in that direction, but that will come into this talk. So I'll concentrate more on the geometric setup. And on the other hand, study of such quantum groups should be intrinsically important and interesting for quantum group theory. I mean, they should give some new examples, and at least a few such examples were looked up. And from the physical side, their irreducibles should have something to do with the physics. These are roughly what I can feel like, and there are some names far from exhaustive, but many of my students, collaborators, ex-students, many of are present here. And again, this is not an exhaustive list, so with which I am working over the last few years on this theme, this general thing. Very quickly, let me recall, because as far as I recall, these definitions really didn't come up. Probably it will help Sutonu maybe also in this talk. But of course, these things in different guides already came up, but not exactly this analytic setup. So let me just recall that what, in the Hronovich sense, what is the generalization of a compact topological group? So that is, as a sister algebra is a unital separable sister algebra. Separability is not that crucial, but let's put it there. and delta is a co-associative co-multiplication to the from A to the minimal tensor product of A with A. Co-associativity condition is this one, and then the existence of the other off-algebraic entities like antipodes and co-units, they are sort of replaced by these analytical conditions of density. And one can prove that, well, I mean, these are equivalent to having those antipodes and co-units on a dense surface. That was Varnovich's work. So each of these linear span is dense, and then you can generalize the group action in this setup naturally. You say that such a pair of CQG, compact quantum group, that acts on a unital sister algebra C, that is a non-commutative space, if there is a unital sister homomorphism from C to C tensor A, which is co-associative in this sense, and the action property, and again a similar density property. The linear span is non-dense. And okay, spectral triple I don't have to really say, already it has been spoken about by many others. Let me still put the slides just to remind some of you, maybe for a few seconds. I don't read it, already it has been discussed. Again, this has also been discussed, where the classical examples come from. They come from the Riemannian spin geometry, and there the commutative spectral triples are typically coming from the spectral triple on the Hilbert space of square integral spinors, or the usual spin-Dirac operator, but and Cohn's formalism is a generalization of that. So now with that, I come into the basic principle of what I mean by a quantum automorphism. Before I go into geometry, let me spend some time on the generalities or the general philosophy of such quantum automorphism. By the way, this is, for example, this is the philosophy of on the earlier literature. For example, Manin took this approach to universal quantum groups and looked at the SLQ2 and other things as sort of universal things in some category. And more systematically, in the sister algebraic framework, it was begun by Suju Wang and then followed up by Debashish and many others. And what is the principle is namely the following. It is simple and natural to conceive of. You are given some mathematical structure. It could be a finite, infinite, whatever. It could be, on one hand, it could be like finite set, a graph, finite or infinite. Or on the other side, it could be a possibly infinite dimensional sister fundamental algebra with some other finite structures, whatever it is. So for the given mathematical structure, you first try to identify the group of automorphism of that corresponding category as a universal object, and then try to explore the similar category where just the word group is replaced by quantum group of your choice. That's the game. That's the rule of the game, the strategy of the game. And just explore whether you get a universal object. If you get that is natural candidate for the quantum universal quantum group or quantum automorphism group for that category or that mathematical structure. Now, this game was, as I said, it started by Suju Wang, Debashish, but they were mostly concerned with finite structures, like a finite set, a finite graph, and so on, finite metric spaces. So, before I go on, so what my contribution or my point of departure was to take this thing to the continuous geometric setup. But before I go into that, let me spend some time once again on their work, which is interesting in its own right. So let's begin with the simplest, the most fundamental one. So what is the analog of a permutation group in this quantum formalism? So you must take an endpoint set, and so if G is the permutation group, then it is nothing but the universal object in the category of all groups which acts on it. I mean, you don't have to, and no one would really define or look at it like this, so it's sort of putting it upside down. But this is the value, and as you can generalize this. If you take that approach, then it is natural to consider a similar category where the objects will be compact quantum groups with an action. So your objects will be, say, Q comma alpha, where Q is a compact quantum group and alpha is an action of the compact quantum group in my sense which I discussed in the beginning, on C of x, where x is this finite set. And if you just write out this in terms of generator relations, because that action alpha, I mean, it's of course a coaction in the half algebraic sense, but as is customary in the Voronowitz theory, because this generalization of group action, this is a dual version of the group action, you still continue to call it an action. But for Hopf algebra, that would be wrong. I mean, it's a coaction on the underlying Hopf algebra on the algebra. So that coaction would have to be written on these generators of this finite set, the algebra of this finite set, which are the indicator functions of the points. So that quantum group will be determined by this Qij, and if you just manipulate with the relations, that namely this chi I has to be idempotent, self-adjoint, they should add up to 1, and also Qij would give a compact quantum group. So you have an antipode and so on. Comparing all these, you can derive the following relation, namely we can prove that this universal compact quantum group does exist and is quite conveniently described by a set of generators Qij, where Qij's are satisfying this so-called magic bi-unitary relations. So these are the Qij which are self-adjoint idempotents, they are projections, and if you arrange them in the row-wise, they add up, they are orthogonal adding up to 1, and column-wise they are adding up to 1. And the universal sister algebra generated by this is actually this universal quantum group. So just defining is not that, it is interesting and quite intriguing, I would say, to discover, well, up to n equal to 1 to 3, this actually will coincide with C of Sn, S1, S2, you will get no genuine quantum symmetry up to n3, but from n equal to 4 almost the dramatic change happens. Suddenly it blows up to an infinite dimensional object. So from n equal to 4 onwards, you have infinite possible quantum symmetries of a finite set, even on a finite set. This is very remarkable, and it may have a physical importance, and that's my feeling is, when I was discussing with some other people, and so it has a very rich quantum symmetry. And well, a similar question you can ask for finite dimensional matrix algebras. So given in Mn, you will look at a category of all pairs Q alpha, where Q is a compact quantum group and alpha is an action on Mn by sister action. Is there a universal object? The answer is actually no. Turns out there are too many quantum actions on Mn, and to get a universal object only along the subcategories, if you fix a function and then demand that action must preserve that function. So here the story is that if I fix any invertible n by n positive matrix, and giving, let's say, this trace Q transpose X gives you a faithful positive functional on Mn, a state on Mn, and you look at the category of all compact quantum group which acts on this Mn, also preserving this particular state, then this category would have a universal object. So in particular, if Q is identity, you would get a quantum group which will contain the SUN, the automorphism group of the matrix algebra, but the other quantum groups won't contain that. They will be in slightly different direction. So that is also very interesting, and these quantum groups, they also can be conveniently described by generator relations for these fundamental unitary representations, the matrix coproduct and so on, and have been studied very nice and very well. Their representation theory, their fusion rules are well known, well tabulated by Manika and others, collaborators. And so is for the quantum permutation group. For example, quantum permutation group, another point which I may mention, very interesting for if you apply to some model, the quantum permutation groups which I mentioned in the earlier slide, for n4 onwards, that is infinite dimensional. They are of course different from n4, 5 onwards. They are all different non-isomorphic, each infinite dimensional of algebras. But the fusion rules from 4 onwards actually the same. The fusion rule actually is very similar to this SO3 or SO2 fusion rule for quantum permutation. So there is some stability on n4, 5 onwards. And whereas your permutation group with n, the fusion rules varies. The irreducible representation set of characters varies from n. It depends on n. But for quantum permutation group n equal to greater than equal to 4, the set of irreducibles and their fusion rules actually doesn't depend. I mean, the category depends, but the fusion rule doesn't depend.
So do you mean irreducibles or co-irreducibles? Do you mean representations?
Co. When I mean co. This is a sort of, I don't know which is kind of parlance or which is strictly speaking not correct. Fine. Right, so again I spent some time on graphs, particularly with the motivation in mind that this may attract physicists. There are many models on graphs. Each of these days we hear many models which are built in graphs, various kind of Potts models and Riemann and so on. So the quantum symmetry of this should be in principle give you something from the physics for the physicists. That's my hope, or that's my proposal, what to say. And just to remind that, well, so what do I mean by quantum symmetry group of the graph? Technically speaking, or is the following. Suppose so given a finite graph with a set of vertices V and a set of edges, then QVE is a quotient of the quantum permutation group of the vertex set. So it should permute the vertex in a way which is compatible with edges, and that is the definition basically. So there is a universal quotient, largest quotient of quantum permutation group of the set of vertices which preserve the set of edges in a natural sense. I don't elaborate on this. I can write down mechanically what it means, but you can sort of conceive what it means. And so this, of course, sometimes it becomes exactly the same as the automorphism group, but most often it is not. And there are a very interesting examples which have genuine quantum symmetries. For example, if you look at this simple cycles, n cycles, then actually only 4th cycle have a genuine quantum symmetry, the square. Others do not. But then for more complicated graph, you can have quite interesting genuine quantum symmetries. The trees will always have quantum symmetries, the graphs which are like trees, for example. A complete graph of n more than equal to 4 vertices will always, there it is just same as the quantum permutation group of the vertices, so that will be again genuine, and so on. So most graphs do have genuine quantum symmetries, some don't. And in fact, you can also construct examples on the recent work of my ex-students, like both of us present here, Shomaldo and No. They were in fact working on some examples of graphs for which you have isomorphic automorphism groups, but non-isomorphic quantum automorphism. So that will tell you that, okay, you may not be able to distinguish two graphs from looking at their automorphism group, but if you can do it if you go beyond the group and look at the quantum automorphism. So there are something which you can see there's some advantages or plus point, plus things. Fine. So again, I'm physically issuing something. I mean, QV is natural symmetry object, should be natural objects, and I don't know how. I'm not a physicist. I don't know nothing, but here are so many physicists and some are even interested in letting down this quantum symmetry and using their irreducibles and to label some kind of elementary excitations or whatever of your physical model. So that's what I should have vaguely feel. This is just a feeling. And another interesting thing which I was discussing with Professor Balachandran, for example, the first we made that this is not on the graph, but the other thing, some other quantum symmetry examples of interesting genuine quantum symmetry are the one's quantum automorphism groups, which I introduced, which are the largest quantum groups acting on matrix algebras, preserving a given state, which comes like trace Q dot, so on. So you vary that Q, that matrix Q, you can actually achieve ergodic actions on all types of von Neumann algebraic factors, which are very important in physics. 3-1, for example, Professor Balachandran was mentioning the other day that type 3-1 is very important in quantum field theory and so on. And in each of these factors, for example, this type 3-1 case, the coaction will come from its realization as Kuhn's algebra, the closure of Kuhn's algebra with the quasi-free state. So that on that you can build the natural action of suitable AUQ. And then on the another possible example could be, of course, the quantum. That was my original vague motivation and still is, like the quantum symmetry group or automorphism group, which we more legitimately call the quantum isometry group, which I'll go in a minute, which on some non-commutative space-time manifolds which model the quantum gravity, that should be giving you information about its fundamental particles, if you believe in Wigner's philosophy, what Wigner did. If you want to carry through a similar program here, and then that's of course a too far-fetched thing maybe, I mean just nothing more than defining these quantum groups, and even that for, I mean I haven't done anything on the Lorentzian side, I mean there's, when he talks in this last 2 days, so whatever formulation I will show you only for maybe the space part of it, only the quantum isometry group of Riemannian thing, of a non-commutative Riemannian geometry. But if that can be extended to non-commutative Lorentzian thing, and then you may have find some applications to real physical models. But well, I mean some application of these were actually done by Francesco Jatishman and Zabrowski. They have at least couple of papers, like 1 or 2 papers I think you wrote, on which they use these things on this cone standard model, computed this quantum isometry group of part of it, a finite part of it, and interpreted that quantum symmetry group in some way. So this is my suggestion, and this is my sort of proposal and dream, whatever you call it, and sort of we throw open to the physicists to take it up and so on. Right. Now let me come more to the mathematics, but again, this is another slide on my sort of not so correct and probably too big dream in the physics side. But so as general principle, what do you mean by this? So if you give me a physical model there, and it's in terms of a Hamiltonian on Hilbert space, then the universal quantum group of symmetry would be the one which act by unitary co-representation in the strictly speaking, but again I call it a representation. So just there is a natural generalization of the unitary representation of a group for the quantum group setup. So I didn't define it and won't define it, but it is not difficult, and it's exact analog of Peter theory, Hertz state, everything is there for this compact quantum group. So you have a well-developed theory, very parallel to classical theory of unitary representation and decomposability of representation into reducibles, everything. So that is there. So here I mean by the unitary representation of the corresponding quantum group of this Hilbert space, which should commute with the Hamiltonian. That is given by that you should call the symmetry of the quantum symmetry of the model. Is there a universal quantum group which have a unitary representation on this Hilbert space of your model, and which commutes, that representation commutes with the Hamiltonian? And often, as we learn from this matrix case, even the finite matrix case, that we have to add the condition that it also preserves certain canonical state. So it may be a state-specific thing to get an existence, and that actually is good, I would say. So that means that you may often get some universal quantum group specific to a state which preserves this state and also preserves the Hamiltonian, the model in some sense. And then if you change from one state to another, the universal quantum group may change drastically, signifying a kind of a state change. So this way one may apply this to some models of condensed matter or whatever. So some reference state change, that's what I wrote there. Some change of this quantum symmetry group by changing the reference state may signify a change of state in the Landau sense. And of course, which I already said, these last few things, that for physical applications it's imperative to extend whatever I've done and trying to do to the Lorentzian setup, but no step has been taken in that direction yet. I think Lorentzian spectral triple are already in its formative stage, but after that this should also be done. At least I'll be interested to do this, for example. So, okay, now after all this introduction or whatever, the rest of the time I will try to concentrate more on the mathematics, more on the precise mathematical formulations, and some results, examples of the quantum isometry. So, what is an isometry in the classical sense? So, the group of Riemannian isometries of a compact Riemannian manifold, one way to look at it is that it is the universal object in the category of all compact metrized group which acts smoothly in isometry. And then what do you mean by isometric action? Of course, you have a geometric definition, but you can translate into the operator theoretic form by saying this is a smooth map gamma on M. It is a Riemannian isometry when only the induced dual map on the algebra of smooth functions, if it commutes with the Laplacian. So it has to preserve the infinity M, that means it is smooth, the map is smooth, then only we preserve that, and if it commutes with the Laplacian, that is equivalent to its being isometric. So in other words, the group of isometry can be characterized as the universal group which acts in a way which preserves infinity M and which commutes with the Laplacian. And you can generalize these things already. I think some talk we hear, and we'll hear more in Jyotishman's talk, for example, about this spectral triples one forms. By the way, in Shanmati's talk you hear something without a spectral triple, the one forms other things. So I believe that everything can be done. Here that this comes as spectral triple doesn't have a much role. So even if you have some other way of defining one forms and have a natural candidate of Laplacian, exactly the same thing can be done. But this is what I actually initially did it, and like this. So for a spectral triple formalism, you under some regularity condition, some summability condition, you can define a Hilbert space of forms, 1, 2 and higher. The very nice description, I mean the best description of this thing which in my view is the best is the Janice book. From there we learn, and I think the space of forms is not written anywhere, everywhere, so, but his book has a very good account of it. So it is highly recommendable to give the details from there. And so you have analogous 1 and 2 forms and higher forms. And so the 0 forms, which are the functions, and 2, 1 forms, this is only you need. So you have a self-adjoint map, you have a map small d closable given by the commutator, and then you can form this minus d star d and call that Laplacian. And under reasonable conditions, which are valid more or less all the usual examples, like of course classical compact manifolds, and also their Raphael deformations, but in many other cases. So many other cases which you use in practice, these regularity hypotheses are valid, and in fact these are also valid usually. It maps there is a natural candidate of A infinity which will be preserved, and it will have compact resolvents with eigenvalue vector belongs to infinity and forming a non-closure subset. And sometimes it is convenient to impose also a connectedness assumption like this. Kernel Raphael is one dimensional. And under this setup, you can define an action of quantum group, compact quantum group on the sister algebra generated by the A infinity to be smooth and isometric if the action preserves that smooth algebra and it commutes with the Laplacian there. So it's in the general setup. They are not now restricted to the classical Riemannian geometry, but in a more general geometric setup, it could be coming from a spectral triple, or it could be even more general, like in Majid's or other top, where you have some natural candidates of Hilbert space of forms and have some operators which is the candidate of Laplacian. Then what I proved in one of my initial work on this, that under those assumptions I listed in the previous slide, you do have an universal object. We denote it by Q iso L, call it the quantum isometry group of the underlying geometry, non-commutative geometry. And assumption C actually can be elapsed. For example, when it is assumption C is a connected assumption, at least for classical and Raphael deformations, you don't need that to have this existence. So, fine. So, that is in terms of the Laplacian. Now, you would like to have also a kind of formulation of universal quantum group which is defined only in terms of Dirac operator, because in a spectral triple that is the basic minimum, AHD. The D is the only ingredient, minimum ingredient. So there also we tried and we indeed defined that. And this may be slightly more technical, I won't go into the full details. Let me just say that classical case, you consider on this part, that in the classical case, if you consider a compact group action on a Riemannian spin manifold, then that G action is an orientation preserving isometry if and only it lifts to a unitary in the two covering of G where it commutes with the Dirac operator. So that means basically commuting with the Dirac operator means isometry as well as orientation preserving, two things together. So this should be the, if at all, this should, in some quantum group which commutes with D, should be called the quantum group of orientation preserving isometry, and its maximum classical quotient should be the group of orientation preserving Riemannian isometry. So that's actually formulated. I don't go into the exact definition, it is a bit technical, but you can see the definition of, for example, the unitary representation of a compact quantum is there. But okay, I don't think I want to spend too much time on that right now. I'll be taking too much time. But roughly this is what is being done. So after the formulation based on the Laplacian, I also have a formulation based on the Dirac operator. For it, usually also have to fix that it also preserves the state. So more precisely, if you fix this data, spectral data with some regularity condition, etc., also some other positive operator and an associated state given by the stress Rx, and then we have a category of compact quantum group whose objects are actually given by the quantum groups. Is called this is Q delta is the CQG, but this is another ingredient, namely a unitary representation on the Hilbert space. So we demand that the Hilbert that U commutes with the operator Dirac operator, and also this adjoint action, and you preserve this trace. If you put all these conditions together, that corresponding category does have a universal object. And these are the analogues of our from the finite matrix algebra those universal quantum group preserved in a state, these are infinite dimensional or general analog of those things. Anyway, this part is very technical, I'll skip that. Now, let me come to how do we, okay, so this is another point which I was speaking, but it should be highlighted actually. The construction and existence proof of these universal quantum groups, these variants of quantum isometry groups, there are also other variants, like you can have a real structure and maybe you demand what is the universal quantum group which is isometric and preserve the real structure and so on and so forth. So all the avatars of quantum isometry groups, if you look at their construction and existence proof, and it can be seen that they actually can be adapted verbatim to any physical model with Hamiltonian with compact resolvents. That compact resolvent is very crucial so far to define this existence of prove the existence of these compact quantum groups as a quotient of suitable free product of unital sister algebras. So without that I don't know whether they exist or how to approach and so on. But whenever this thing is true, if a discrete spectrum, then you can have a universal thing. And actually such a general framework was written by, was identified and read by the Bunnigan-Skalski's paper, and they gave it the name of quantum symmetry group of orthogonal filtration, and under which is more or less, it has to be extended a little bit, and once, I'm forgetting her name, and this who did it for the Hilbert model. Chevron, right, so a student of Bishon, right? So there's a further work to extend it a little bit to capture all the quantum isometry groups, but that was also done. So there is sort of quantum filter, a slightly more general setup of orthogonal filtration of Hilbert modules in which you can accommodate these quantum isometry groups nicely. So fine, so that is mathematical part, but how do you compute these things? Most important will be the compute examples, and so after defining and proving existence, we did venture to compute, and we did compute it, and there are two basic principles which helped us compute. One was, the first is this, how they behave with cocycle deformation. So Riffel deformation or more general cocycle deformation. And as we'd expect, it turns out nicely that the functor of quantum isometry is and the functor of deforming the commute. Put it in a more elaborate word, it says that you compute the QI. So by QI, so I generally mean all of these. Quantum isometry group depending on Laplacian, or in the Dirac operator formalism, or in some other setup like preserving real structure, so on and so forth. So all such quantum isometry groups of a deformed spectral triple. If you start with the spectral triple and you have some natural group actions and also a cocycle, and the Dirac operator has some compatibility with that action, then you can deform to make it a non-commutative algebra. A theta is the simplest example, but you can generalize that. And in the general setup, it turns out that for the deformed spectral triple, if you compute the quantum isometry group, that is isomorphic with the deformation of the quantum isometry group of the undeformed one. So in a similar way, you can define deformation of a compact quantum group by some cocycles on its abelian subgroups, abelian or more general subgroups. So that I mean by the deformation of the quantum group, cocycle deformation of the quantum group. So it turns out that QISO of the cocycle deformation of the triple is isomorphic with suitable cocycle deformation. So the cocycle used to deform this spectral triple and the cocycle used to deform this quantum group are of course related. Given a cocycle, out of that you can sort of define the cocycle which you need to use for deforming QISO. So this gives a very handy way to compute many examples. If you know their QISO for classical things, I'll come to that later. So if you know how to compute QISO or what are QISO of the classical Riemannian manifolds, then you know what are QISO of all Riffel deformations of classical manifolds. So it's a very, very big class. And on the other hand, other type of examples in noncommutative geometry which comes as an inductive limit of finite structures, built on finite sets, finite graphs, and so on, they are the inductive limit, and for that you need to study how QISO behaves with inductive limit. And again, it turns out very nicely that under some mild condition, natural and mild condition, functor QISO also commutes with the functor of inductive limit. So I don't explain exactly what full details what I mean by inductive limit of spectral results and so on, but you can sort of vaguely visualize what it should be, and you should properly write down what I exactly mean by this. So it should be some families of a sequence of spectral triples. Nth is related to n plus 1, embedded in n plus 1 in a natural way, so on. So if you consider such a setup, then QISO of such limiting spectral triple would be isomorphic with the suitable limits of these quantum groups, and that will help us to compute QISOs of many AF algebras, many models on the AF approximately finite dimensional system algebras, on Cantor sets, trees, and so on. On the graph, for example, I mean, discrete graphs, if an infinite discrete graph you want to compute the quantum symmetry, you can truncate it, and there Manika, Ambisho, and many others is computed a lot, for many such graphs, and in principle you can glue them together, and the inductive limit, and in the limit you will get the QISO of these infinite graphs. So this is another very useful tool to compute. And then this brings us, as I said, that QISO of deformation of a classical thing is same as deformation of the QISO of the classical things. So the basic thing you have to know is what is the QISO of classical? Is it same as ISO? Is there a genuine symmetry? This is a natural question. And we, of course, from the very beginning we went on computing, and for example in Jyotishwan thesis, and then later on, and we put our hand on various, we and others also computed, and finally the examples were suggesting that, well, if you have a connected Riemannian compact manifold, then the quantum isometry should be same as the isometric group, C of the isometric group, but it took quite some time to actually finally prove this theorem. So this came up finally with Somalo thesis with him, and this has now actually appeared in GAFA, geometric function analysis. But this is actually a quite intricate, various differential geometric techniques done into it. I mean, it's very non-trivial to I would say. But the theorem finally comes. So it is a Q iso L of C iso M is C iso M for a compact connected Riemannian manifold. And very recently, this I have posted in the archive, but it's not yet published, but I actually went on further and proved that you cannot even expect a smooth action. Like if a CQ GQ acts faithfully on some continuous function algebra of manifold, where M is a compact connected and smooth manifold, the action also smooth in the sense it leaves invariancy in phi M, then Q must be equal to C of G for a compact group. So there is no genuine quantum smooth symmetries of a connected smooth. So this coupled with the fact that QISO commutes with deformation, you get QISO of all non-commutative manifolds at one go. Whenever you have a connected Riemannian manifold, you have some natural co-cycle or group actions to deform it. You know what is QISO of this deformed families or deformed non-commutative manifolds. These are just deformations of this, long deformation of this QISO of the ISO group, the C of ISO. Here, though it is not exactly related to the main theme of quantum isometry, but more mathematical, but I am sort of tempted to say a few things, that this brings us to the question of are there genuine quantum symmetries of classical spaces? I mean, space by space you can even mean, it can be an algebraic variety if you like, if you are more algebraic, it can be smooth manifold if you are more geometric and so on. And it actually is independently investigated by a group of people, Pavletinkov, Chelsea, Walton among them, from a purely algebraic point of view, and they came up with a very similar algebraic theorem, but on a very finite, for a finite dimension of algebra action. Finite dimension is very important, tailor-made for their construction. I won't describe that their result, but as mentioned that there was a purely algebraic no-go result in the similar vein, so on. But for my setup, for the geometric topological setup, we have the following. So we have the no-go theorem for smooth compact quantum group action on classical manifolds, and three things are crucial: connectedness, compactness of the quantum group, not so much compactness of the manifold, but compactness of the quantum, and the smoothness of the action. For example, you can have for connected compact metric space, which is not smooth manifold, which are like this, for example, which are this enclover type sets. If you have four or many such things glued together topologically, not smoothly. If you make it smooth gluing, then the action which won't extend. But if you have a connected compact metric space constructed out of gluing such, say, interval at a point, then and four or more of them, then you have a natural quantum permutation group of 4 acting on that. So you have genuine quantum acting on such things. So this is a non-smooth but compact connected metric space. So yeah. And on the other hand, if you look at the more algebraic, in an algebraic, it comes with a variety written there, just a cross x, y, 0. On that you can even have a very nice finite dimensional compact quantum reaction, sister of S3X. This actually is also very straightforward to write down. For example, so yes, so this xy equal to 0, this is the variety. And if you look at the sister of the permutation group of 3 objects, S3, but sister algebra of that, convolution algebra. So that is a non-commutative, as an algebra it is a non-commutative because it's like this C of group. So it is generated by, for example, the transposition. You can think of this 1, 2, 1, 3, these 2 transposition, the 3 objects, they will generate the whole S3 group, right? And they will be non-commutative. And this is given by your canonical coordinate variable x and y, and you just algebraically send x to x tensor, say delta 1, 2, and y to y tensor delta 1, 3. That will be faithful because these two together generate the whole group algebra, which is a non-commutative. So you have a genuine CQG, if you like, finite dimensional, acting on that connected but non-smooth variety. So that this counterexample tells you that in the no-go theorem, so but if somehow, if you have a smooth thing, everything is smooth, connected, and you demand a smooth action, that conspires to prevent your compact quantum group action. Well, no, this may be too far-fetched, but something like that, well, you have genuine quantum symmetry in the model which is discrete. Discrete may have some quantum nature, but something which is too smooth, maybe too classical, don't expect anything which is non-classical. And maybe this is, I don't know whether this should go by this or not, but very philosophical, I would like to interpret it like that. But anyway, the third thing very interesting, that even for smooth, very nice varieties, even for polynomial algebras, you do have Hopf algebra, genuine Hopf algebra coaction, which is associated with a non-compact type quantum. For example, quantum A star B. And very other by cross problem. We have a paper A Sudono, for example, where we wrote some class of examples that type. So the model is, if you allow non-compact type quantum groups or the associated Hopf algebra, you can have genuine quantum symmetry even of very smooth, nice manifolds or varieties. But for compact quantum groups, your choice is restricted up to only for this kind of. Okay, so I'll spend another 5 minutes, right? 5 minutes. I think I'll now spend that on the examples. You should see something which are concrete examples, and here are they. For A theta, I already explained that, the A theta is spectral triple. But again, the collection of that, so here the Laplacian, which already appeared in a different guise of energy function and so on in the stuff, but if you like, this is the Laplacian on this model. And there, what is the maximal quantum group which can preserve this Laplacian? It is this, which is a direct sum of 8 copies of sister algebras. 4 of them are commutative and 4 of them are non-commutative. I didn't write the co-product, but I can tell you that this is actually a deformation, as the general theorem says, of the isometric group of the two torus, which is a semi-direct product of the usual smooth, group symmetry, the T2 itself acting on itself, but coupled with a semi-direct product with the 8-point discrete group, which consisting of your if you take the conjugation of 2 coordinates, or you flip the coordinates, the 3 possible things, x, z going to z bar, w going to w bar, or z w flip to w z. So this 8-point finite group with semi-direct product with T2, that is the group, and this has been deformed here into a quantum group. This is a genuine compact quantum. This is a maximum quantum symmetry of a theta model system. And if you look at the D only, then actually you don't get anything other than that T2. To demand that what is the maximum quantum group which has a unitary representation and lives to a unitary representation on this Hilbert space commuting with D, then actually it turns out to be only classical. And then the next example is the Goswami SUQ2 and so on. You can recall with this generator relations and this coproduct on the generators. And there are many spectral triples. There's one which nicely constructed by Rani Landy and his collaborators, which were actually bi-equivariant, but this was not the up one, it was the earlier one constructed by Chakraborty Pal. But here it was just simple to describe, so I just wrote it down, the compact quantum group. So here, as you expect, that corresponding, for this corresponding spectral triple, the Q iso turns out to be the mu deformation of the unitary group. For SU2 you get U2 in this context, and it's as expected that SU mu2 would give you mu2. However, for such Dirichlet deformation we didn't have it the general theorem. But so this is a more case by case. So the Dirichlet deformation was covered by your general theorem, whereas this type of Dirichlet twist, which is non-equicycle one, is not yet covered. So here you have to do it case by case, but it sort of suggests that probably a similar theorem should exist here also. But we didn't yet try or didn't yet succeed. And put the sphere again in the expected line, but you have to compute and prove that it is the one you will expect. So namely, there is a natural spectral triple on this, for which if also the natural restriction of the hard state on the Poisson sphere. If you demand your largest compact quantum group which commutes with the Dirac operator and also preserves that restriction of hard state, to get the universal one, and it can be seen to be isomorphic with SO mu3. So here again, I mean, if you for S2 it is the SO3 and for S2 mu it is SO mu3 comes out. Again, so it seems that there should be a general theorem even for non-cocyclic deformation. This example that we said. Okay, I think I'd like to stop there. Thanks.